Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all to the class of real analysis by Walter Rudin. In today's lecture, we are going to start a new chapter from this book, Numerical Sequences and Series. This chapter is very important for your final exam. In this video, we will discuss the basic concept of convergent sequence and bounded sequence, and we will see some important examples given in the book. So let us start. This is definition 3.1. This definition is about convergent sequence. In this book, we will discuss this definition with the relation of metric spaces because the chapter number 2, that is actually the basic topology. So Walter Rudin is defined all the definition related to metric spaces. So in terms of metric spaces, a convergent sequence can be defined as, he says, a sequence Pn is a metric space in a metric space X is said to be converge if there is a point P belong to the set X such that for every positive real number epsilon, there is an integer n such that the metric D is less than epsilon. Here D denotes the distance in X. In this case, we also say that Pn converges to P, or that P is the limit of the sequence Pn, and we write it as Pn approaches to P, or you can write it as limit of the sequence Pn as n approaches to infinity is P. So this is the simple definition of convergent sequence. Intuitively, we say a sequence converges to some number of a given set X if all of the terms converges to approaches to that numbers. Usually, in some books of real analysis, the author defined the sequence definition of convergence of sequence in term of real numbers, and they use oftenly usual metric. But Rudin is using the broad concept of convergence of sequence. He says if D is any metric, then a sequence Pn is called convergent sequence if the distance of the sequence, the distance of the terms of the sequence from a specific number P is less than some positive real number epsilon, then we say this sequence is called convergent sequence and converges to the number P, and this number P is called the limit of the sequence. Next, a sequence which is not a convergent is called a divergent sequence. If Pn does not converges, it is said to be diverge. Here, one of the important thing that you can notice here, the definition of the convergent sequence does not depend on the sequence Pn, only on Pn, but it also depends on the ground set X on which you have defined the metric. For instance, the sequence 1 over n, this sequence converges to 0 in set of real number R, but it fails to converge in the set of all positive real numbers with the usual metric dxy is equal to absolute x minus y, where xy belong to the open interval 0 to infinity. So the convergence of sequence depend on the set X also. Next, the important definition is a bounded sequence. If you read Robert G. Bartle book or Tom Apostle, or any other book of real analysis, a bounded sequence can be defined as a sequence xn is called bounded if its absolute value is less than or equal to some positive real number m. While Rudin defined the definition of bounded sequence with the following lines, he says a sequence Pn is called bounded sequence if its range is bounded. If its range is bounded. This definition is equivalent to the earlier definitions of bounded sequence. This is not different from this definition also. Here m is a real number and greater than 0. Now the definition given in this book is same as this definition because in chapter number 2, basic topology, Rudin defined a set E, a subset of R is called bounded if there exists a positive real number m such that every element of set E is less than or equal to some positive real number m. So when you say the range is bounded, it means you are saying that the element of its every element of this range is less than or equal to some positive real number m. This is the same concept that I have discussed here. So a sequence is called bounded if its range is bounded. For example, consider the sequence of complex numbers. This is the first example. Your sequence is Sn is equal to 1 over n. This is the nth term. Why does he call it as a sequence of complex number? Although you can see its every term belong to set of real number, because you know every real number is a complex number. So Rudin broadly says it as a set of as a sequence of complex numbers. Now we have to check whether this sequence converges, whether it is bounded or unbounded. The nth term of the sequence is 1 over n. If you take a limit n approaches to infinity, then its nth term approaches to 0. So this shows that the sequence converges and its limit is 0. Further, the range of this sequence is, if you plug in the different values of n here, we get the set of values. For n is equal to 1, this gives 1. For n is equal to 2, this is 1 over 2, 1 over 3, up to so on. This is this range of the sequence. Now this range is bounded set, so the sequence is bounded. How this is bounded? You can observe that every term of this, every element of this set is always less than or equal to 1. So this is my m. This is my m is equal to 1, for which every term of this, every element of this set is less than. So that's why this range is bounded, and hence I can say that this sequence is bounded sequence. While on the other hand, if you consider Sn is equal to n square, if you take its limit n approaches to infinity, this approaches to infinity, this shows that the sequence is not a convergent and hence it is a divergent sequence. Further, this sequence is unbounded because if you find the range of the sequence, this is an infinite set. For n is equal to 1, this becomes 1. The second term is 2 square, this is 4, 3 square, 9, up to so on. So this set is an infinite set, and it is also unbounded because you cannot find any real number m that can bound all of these terms. Because whenever you increase n, your range values will also approaches to infinity. So you cannot bound all of these values with some positive real number m. So that's why this sequence is an unbounded sequence, and also it is a divergent sequence. The third example is Sn is equal to 1 plus minus 1 over n. When you take limit n approaches to infinity, clearly this is a constant term 1. So when you apply here limit n approaches to infinity, it depends on the nature of infinity. If you take limit n approaches to infinity, this becomes minus 1 over n whole power n. Either your n is sufficiently large, even or odd, this becomes infinity. This is some number, either it is minus 1 or plus 1. In any case, this becomes a 0. So this limit becomes 0, and hence 1 plus 0, this is equal to 1. This shows that the limit of this sequence is 1. So sequence convergent. The range of the sequence is a bounded set. If you find the terms of this sequence by plugging different values of n, the first term is 1 plus minus 1 over 1. This is equal to 0. Similarly, when you put n is equal to 2 here, this become 1 plus 1 over 2. This is equal to 1 3 by 2. So you can bound all of these terms. So the given sequence is a bounded sequence. The next one is Sn is equal to iota raised to power n. This is a complex valued sequence. Here the range of the sequence is only the fourth root of unity. When you put n is equal to 1, this is iota. For n is equal to 2, this is iota square, this is minus 1. For n is equal to 3, this becomes iota cube, that is minus iota. And for n is equal to 4, this becomes iota 4, this is equal to 1. And for any other integral values of n, this will repeat these values. So the range of this set is a finite set, and finite set is always bounded. Hence this sequence is a bounded. Further, whether it converges or diverges, this sequence is a divergent sequence because for the different values of n, the sequence assumes one of the value of the range, so limit is not unique. So sequence is divergent because the existence of limit is also depend on that the limit should be unique. So although the limits, there are the only four elements in the range, but the limit is not unique. So that's why we can say that this sequence is a divergent sequence. This is a constant sequence for any positive integer n. Each term of the sequence is always equal to 1. So the range of this sequence is a singleton set, that is a finite, and hence it is a bounded. Further, limit of the sequence is always 1, and hence it is a convergent sequence. So in today's lecture we have discussed the concept of convergent and bounded sequence. I hope now you have a clear understanding about both of these concepts. Inshallah, in the next lecture, we will discuss a very important theorem 3.2, and this theorem is also actually related to the boundedness and the convergence of a sequence. So if you find this video helpful, kindly like, share and subscribe my channel. See you in the next lecture. Take care. Allah Hafiz.